Okay.
Okay. So good morning, everyone. As usual, of our weekly AI talks, today we have a talk by Professor Zhou Wang from the University of Waterloo. Professor Wang is a Canada researcher, and in addition to being a university professor, he is also the co-founder of a successful startup company called SSIM Wave, which offers technology solutions to media, entertainment, and telecommunication industry. He is also a pioneer in the field of image quality assessment, and he has written several important papers in this field, which kind of opened and expanded this field. He is a fellow of IEEE, Royal Society of Canada, and Canadian Academy of Engineering. He is a recipient of the 2014 Stacy Memorial Fellowship, which is awarded by the Governor General of Canada. And in addition to academic success, he is also a recipient of Technology Emmy Awards. And by the way, twice, once in 2015 as an individual, and another time in 2021 by the company he has co-founded. Today we are going to listen to his talk titled "Addressing the Data Challenge: Model Comparison with Few Samples." During the talk, if you have any question, you can use the Q&A tab, and I will try to ask your questions on your behalf. And by the end of the talk, we'll also have Q&A, which you can ask questions individually. And I guess we can start, or maybe can we wait maybe 1 more minute? And also on another note, you can also see that speakers in the coming few weeks, and hopefully we are going to see you again in the coming weeks.
Okay, Dr. Wang, you can share your screen.
Okay, so can you see it?
No.
Not yet.
No, not yet. Okay, let me try it again. Okay. Share.
Yeah, we can see it now.
Is it good now?
Yes, and I think you can start because we waited.
Great. Thanks very much for Mohammed's introduction. Obviously I have known Mohammed for quite a long time, so it's good to see him again. It is my pleasure to get this opportunity to present some of our work and basically some of our recent ideas and thoughts. Right. So today I'm going to talk about addressing the data challenge, model comparison with few samples. So before I go to the subjects, I would like to have a very brief kind of introduction about our background. So I'm directing a lab called Image and Vision Computing at University of Waterloo. So basically the lab is working on 3 general topics: image and video processing, perceptual modeling, and machine learning. So basically any topic that kind of is the intersection of the 3 areas would be the interest of our lab. The lab has been working on many different research projects mostly in perception, visual perception related image processing and computer vision and pattern recognition problems. We're also working on some topics on, say, 3D, multimedia, AR, VR kind of stuff. So I would start to kind of give an example about one of the major problems our lab is trying to solve, which is image and video quality assessment. And this is actually, for most people who may know our lab, this is how they get to know us, right? So because of our work in the area of image quality assessment. So here I'm giving an example. So on the top left is the original Einstein image. And at the same time, you can see 5 altered versions of Einstein. And one common thing of all these 5 altered versions is that they almost have the same mean squared error if you compare each one of them with the original top left image, right? So basically, mean squared error is saying that all these 5 images have the same level of distortions or the same level of quality. That's a major problem, because when you actually look at these pictures, the perceptual quality of these images is drastically different, right? So, which means this simple numerical computation that has been used very, very widely in the field of image processing and computer vision for quality assessment, for a comparison of algorithms, and also for optimization for algorithms. So this simple numerical method, if that cannot reflect the perceptual quality of an image, then probably we have been doing the wrong thing when we do when we compare different algorithms and when we optimize for these algorithms. So the idea of the motivation of perceptual image quality assessment is that can we come up with an objective model that can predict perceived quality. So for example, here I'm showing one example of SSIM that is giving much higher scores to the top 2 images than the bottom 3. The bottom 3 looks really bad in terms of quality. And of course, structure similarity has been published in 2004. It's already like more than 14 years old, 17 years old. So in recent years, there has been a huge literature on image quality assessment, and there's a lot of improvement on top of that. But we can think about structural similarity as a kind of a starting point that people are looking at some also very simple method, but reflect certain perceptual properties of the human visual system and trying to do a better prediction of image quality. So just to move on a little bit further, so what's the actual use of image quality assessment models? Actually, there are many different applications. Obviously, in any image processing and computer vision applications, either implicitly or explicitly, you're gonna have somewhere in your, when you develop an algorithm, a system, or you deploy a system, you kind of implicitly or explicitly are using some image quality measure somewhere. It's just that sometimes you don't even notice that. So if that's the case, then any improvement in terms of predicting image quality is going to have impact in all these image processing and computer vision field. And I believe this is probably one of the major reasons why the work, the improvement in the field of image quality assessment is attracting so much attention, and a lot of people are following that and trying to use them for different applications. So here I'm just giving you one very obvious and very useful, strong application of image quality models. So here we call the quality of experience assurance in video distribution. Say, for example, you are creating like a video sharing service, right? So in the cloud, right? So then basically you start with a certain source content, and then you need to kind of at head end process the content, encode the content, and put into a media center that is transcoding that content and packaging that content and store that somewhere. And then this content is going to be requested by certain users and then being sent through the network and finally reach the consumer devices. Right. So the whole workflow looks like this, but the main question is, how can I ensure the quality of your video is kind of preserved through this long kind of process of video distribution? Right. So basically, the question is how to assure end users quality of experience, but there are also other questions. So how to assure content producer creative intent is preserved, right? So in the past years, we also have a lot of chances to talk to content producers, like guys in Hollywood, right? So when we talk to them, they have huge concerns about this preservation of creative intent, because they spend so much time and effort to trying to make every single color, every single pixel in their video content to reflect certain effect, right? So, but they say once they deliver their content to video distributors, it's completely out of control. So there's no way they can say, okay, this is not right. And many of them just hate to watch TV at home because their own content got delivered to consumer devices. Then the quality of the stuff has been changed completely. So that's according to our discussion with Hollywood guys. So how to preserve the creative intent of content producers is also a very important factor here. So another thing is these video distributors won't spend infinite amount of money on this distribution service. So the thing is, how can we maintain the quality of end users QoE and also do a good job preserving the creative intent of content producers? At the same time, we can save some money, right? So we don't want to use infinite bandwidth or network resources to kind of deliver this video, right? So these are the real challenges. But all these challenges are kind of start with the question, you have, in order to optimize your system, you have to be able to kind of measure its performance. And because the ultimate receivers are the human eyes. So human eyes would have the final say about the quality of this video, right? So there's actually an ultimate, I think I call this ultimate solution. Actually, it's very simple for quality assurance in video distribution. So suppose you have this long chain of video distribution system, and what you can do is to put some people at every single transition point in this distribution system. These people have had to be sit there and watch the video stream going through them 24/7 and all the time, and then report the perceptual quality to you. And suppose you have a center location to collect this data in real time, then you pretty much have a very good sense about how the distribution system work. And of course, in order to implement this is too expensive. So you don't expect people can sit there 24/7, and different people have different kind of opinions and different mood and so on. So you cannot expect them to kind of produce consistent assessment. And considering a large scale video delivery system, you could have thousands of channels and millions of users. So you can't imagine putting all these people sitting there just to watch the video content for you. So then this comes to the usage of the application of image and video quality models. Suppose we can create some probe, or what we call the QoE probes, to replace all these humans sitting there. And these are just the algorithms running in real time. And then you collect all these quality of experience assessment at all these transition points in the center location. You still got a very good sense about what's going on in this whole video distribution system. So that's the first step of quality of experience assurance, right? So because once you have that kind of data, You can do end-to-end QoE monitoring, and then you can easily do failure recovery, because you can look at these scores, and if the score drops significantly at certain kind of module, before and after certain module, then you know there must be something wrong there. So it's easier for you to locate the problem, and that's the first step of recovering and solve the problem. And you can also use this as a framework to optimize your video encoding, video streaming, all kinds of optimization work you can do. And of course, when you collect all these data for a long time, you also automatically create big data. So maybe you can do some strategic planning about how you're going to kind of drive or control your video distribution system. Right. So that's basically the usage. And of course, at the core of this usage, in order to kind of enable this application, the key thing is to create an objective image quality model, right? So this model has to kind of has to produce a score that is as close as possible, just like humans. So just like humans are seeing that, if the humans say, okay, the video here is excellent, then the algorithm is supposed to, the model is supposed to predict that the quality of the video or image is excellent. If the subject say this is a poor quality or bad quality or unacceptable quality, then the model should also be automatically detecting those. So even only when you have a model that is as accurate as that, then this can be used in real life. So that's why, and obviously this is a very difficult problem. Anything that you want to predict how humans think about certain things is, I guess it's automatically a very difficult problem to solve. So that's why there are so many papers in the past 2 decades dedicated to image and video quality assessment. Just to give you a little bit more kind of background.
Here's a question.
Yes?
Sorry. So the question is, because you just talked about the metrics, what if we apply a simple metric to the JPEG binary, like as a simple solution? Would it work?
JPEG binary. So basically here if you have a JPEG image, right? So you can decode that JPEG image to a picture, and then this is exactly the right slide. You have different ways to do to run the model. The full reference model, basically in that case, you have the original image without compression to compare with. So when you assess the decoded JPEG image, you can compare with that. That's relatively simple, but you also expect a higher accuracy of your quality prediction. But there are also other models like no reference and reduced reference model. In the case of no reference model, you don't even have access to the original image. You're given this JPEG image, then you are asked to assess the quality of that image. And there are also a third type called a reduced reference. In that case, you don't have full access to the original image, but you are allowed to extract certain features from that picture, right? So suppose you have very low bandwidth, send a few features about the reference image, and then you make use of that as side information when you assess the quality of this compressed image. So in general, for JPEG compression, is if you look at the literature, it's a relatively easier task. If you know this is JPEG, then it's relatively easier, and there are different ways to do that, right? So I think we have already achieved quite high quality prediction. If we know this is exactly JPEG, about 20 years ago, we are already kind of achieving pretty high accuracy. The more challenging thing is what we call the cross distortion type and cross content type kind of prediction. How you make consistent scoring across distortion type of content, that's much more difficult. Meaning that, say, for example, you're doing a no reference measure, and you don't even know what kind of distortion it is, right? So you could have noise, could be blurry, could be have blocking effect, could have some other fancy artifacts, right? So and you want the algorithm to automatically figure out what kind of the quality of that picture, or maybe even figure out what kind of distortion is in there and how severe are these distortions. So that's going to be much more difficult problem, right? So that's the when we look at the literature, that's the kind of interesting point. And the literature in the early days, people focus, especially in the no reference case, people focus more on application specific, like just JPEG or just blur, right? So and but later on, people move to more and more challenging problem. People put all kinds of distortion together, trying to have a joint model, a unified model to predict all kinds of distortions. Yeah, hopefully this answers the question.
Thank you.
Yeah, and in terms of the approaches, people are using to do image quality assessment. Generally speaking, there are two different schools of thoughts and ways of doing things. The first is called the knowledge-driven approaches, right? So the second is called the data-driven approach. So they're very different. So the general philosophy is very different. So knowledge-driven approaches believe that in order to predict image quality, we have to understand human eyes first. We have to understand how humans how the visual system process these images and trying to dig out how humans make judgments about image quality, right? So it's also useful to have knowledge about the natural image statistics. That's basically based on the assumption is that the human visual system is at the current stage is because it has gone through a long time of evolution and development from case or adaptation to the short-term adaptation to the visual environment. So the visual system is kind of adapted to the environment. And what is the environment? The environment is actually natural thing, right? So if you have like a good understanding about natural image statistics, you can assume that the visual perceptual kind of process is kind of a dual problem, such that if you have a model about natural image statistics, you can apply that model to predict how humans would behave, assuming humans are highly adapted to the natural visual environment, right? So, and if you look at literature and both kind of things, actually there are third kind of knowledge. Third kind of knowledge is about image distortions. Suppose you know the distortion process. So for example, I give the example, if you know this is JPEG compressed, right? So then you can make use of the knowledge because JPEG compressed, you can expect there are blocking artifacts, for example. Then you can just detect that blocking artifact. That pretty much give you a good prediction about the quality of that image. Right, so and the thing is, if you look at the literature, especially if you count the papers more than 10 years old, for example, most of the papers are kind of either go into one of these categories, knowledge about human visual system, knowledge about natural image statistics, or knowledge about image distortions, or some combinations of two or three of them, right? So if you count all the papers more than 10 years old, right? So that's at that time, people just believe you have to understand the physical reasoning behind that, why image quality got degraded, and you have to kind of understand that in order to have a model to predict that. And then later on, of course, that's ENN and all those kind of things is changing the whole world. And obviously, it's going to change the field of image quality assessment. So in the past 10 years, you see more and more paper on data-driven approach. So in this case is that, okay, I have no knowledge about human visual system. I have no knowledge about even image statistics. I just don't know anything. So all I have is I have a bunch of images, and hopefully I have scores. I have ground truths about the quality of these images. Then all I need to do is to design some machine learning approach. Just throw my data. Input, output. Input would be images, output would be quality. You just throw your data, suppose you have enough data, and then train a model to predict image quality. And hopefully this model can extend to new images in the future, right? So, and of course, if you look at this, there are different types, and in terms of machine learning method, you could have the feature extraction step, and then in the feature space, you kind of create a model, and or recently you have more end-to-end model, right? So you put the DNN there, right? So you have input and output. You don't even look at things in image, you just train that. And of course, there's in terms of the principle, there's no difference between the two, because when you look at the middle stages of any DNN, you can call the middle points as features as well. So there's no fundamental difference there. But just now, people have more end-to-end training models in the past 5 years also. Okay, so that's basically two very different approaches, and knowledge-driven, data-driven approach. And here, actually in this talk, we are more concerned about this data-driven approach. And this is, of course, more related to the field of machine learning. And in the field of data-driven approach, if you think about, okay, how to use this data-driven approach to solve image quality assessment problem. So basically, you follow this very simple step, straightforward. First, you need to construct image database for image quality assessment. Database has to be like, first you collect image samples, you collect many, many images. And then second thing is you label these images by subjective testing, right? So because only the humans can give you, supposedly, only the humans can give you ground truth about the quality of these images. But then we are facing, this is the major this get into the major problem that we want to talk about in today's talk. The major challenge is subjective experiment is super expensive. For image quality assessment is even more obviously more expensive than object detection, object recognition kind of task, because for image quality assessment, it's really hard to get consistent scores if you don't control the viewing environment of the subjects, and also subject response have much bigger variance than other tasks like object recognition, right? So people have different opinions, and just because of the screen, the visual environment, the lighting condition are different, people may also give different scores. So far, most of the most reliable subjective testing are kind of lab controlled environments. You can have very consistent lighting conditions. You control the viewing distance between the subject and screen, and then you also control the size and the image on the screen, and so on, right? So then you got a very consistent environment, and then you give consistent instruction before the experiment. In that case, you get relatively stable, consistent scores from subjects, and also people have different suggestions. But the ballpark idea is that you have to have like 20 or 30 subjects to score the same image, at least, right? So you can have more, but at least 20 or 30 people to score an image in order to get that consistent and reliable score about the quality of that picture. Right, so then you can think about this. This is going to be super expensive. So in the end, when you look at the real database that in the literature, people call a database with 1,000 images with very large scale data set, right? So, and in early days, people have fewer than 100, and then a few hundred, and now then we have over 1,000. Recently we have over 10,000, but that's super expensive. You need a long time just to collect that data. So because of subject experiment is expensive, so you end up with a small number of samples. But this is versus like a large prediction domain. So because if you think about the images, if you think about, say, images with 1 million pixels, then each pixel is a kind of a scalar value. Then if you put all these together, you're basically living in a 1 million dimensional space. You can imagine you have a few thousand samples in a 1 million dimensional space, and you're trying to train a model to do a good prediction. Then you kind of suspect about what you're gonna get. Am I guaranteed to get some overfitting problem, right? So how can I make sure my data, maybe I'm hoping that my few thousand sample is a good representation in terms of the distribution of the data in this prediction domain, but how can I know that, right? So how can I prove that, right? So this means that it's very easy, you got some overfitting problem. And this is exactly what happens, right? So when you look at the literature, for now, if you look at the field, then we already have many image database, 10, 20, 30, so different databases. And the very common case is that if you train your model with one data set, you try another data set, the performance drop a lot, right? So especially for those more realistic data set, is very challenging. It's not that machine learning doesn't work, it's that the data doesn't work, it's not enough. You don't have enough data, you don't have the same distribution, same representation, the good representation of the prediction domain. So that's the major problem. So that's basically the major challenge we have in the field. All right, so and not surprisingly, people propose different methods to meet this data challenge. And very straightforward and obvious thing you can do is to do data augmentation. You can rotate the image, you can flip the image, you can crop the image, you can do all these kind of things just to kind of make my trainings, increase the size of my training sample. And this helps a little bit, but not really a lot, because if you flip or crop a picture, it's still kind of the same content, right? So it's not really helping that much of image quality assessment. And you can also think about the transfer learning approach. Suppose I train a model through other tasks. So for example, by object recognition task, and then I have a trained model and start from there, I use transfer learning to learn a model, right? So there are some progress on that. And there are also kind of controversial, some argument about whether this is the right approach. Some people say, prove, okay, this is very useful. I use the feature obtained from object recognition and using that feature as a starting point, and then I train like a refine model, I got pretty good result. Some other people argue that the object recognition and perceptual quality assessment are very different tasks. How can you know the features can be reused or it has to be similar, right? So there are quite a lot of arguments and also inconsistent data and people, right? So if you have a point, you want to prove it, you always find the data to support yourself. So if you look at in the literature, so there are some argument, right? So you can also have some other ways, say leveraging from other ground truths. So for example, you can have multitask learning and rank learning and replacing subjective data with synthetic benchmarks, which hopefully to be cheaper. So I'm just going to a little bit example, hopefully quickly of that. So you can have multitask learning. So for example,
there's a question before you move to the next
please.
topic. So, so does the evaluation need original image?
Evaluation, you mean image quality assessment, subjective testing? In subjective testing, actually there are, yeah, that's another thing actually pretty makes things more complicated, because the subjective testing protocol, there are several different kind of standard protocols. There are protocols that just look at the picture itself and then give a quality score. And then you can also put your reference original image as one of the test image. But in all these cases, you kind of random kind of put all these testing images together. The testing image include very distorted image, but also the original images. But when people give score to individual one, they don't compare with anything. And there are also subjective testing. You kind of compare two images originally, tell them this is the original, this is the distorted, or you have a video, you play the reference video first, and then you have the distorted video, and then ask them to give scores. There are also variations in terms of protocol of subjective testing. Actually, the subjective testing for image quality is a very complicated field. when we start with this, we thought this is something simple, but actually it's a very complicated process. There are also a lot of strategies how you can reduce number of subjective comparison and so on, right? So of course, there are also kind of ranking kind of subject testing or kind of two alternative choice and say just pairing and say which one is better, right? So there are so many different variations of subjective testing. Hopefully that kind of answered the question. So here I'm talking about the first method about the multitask learning, right? So that's kind of like a transfer learning. The thing is, you basically have two subtasks. The first is, let's just do a classification. I train a model to do distortion classifications, right? So for example, you got a data set. It includes all kinds of different distortions. You have noise, you have JPEG, you have JPEG 2000, and other distortions. And then you first do a classification, because the classification labels, the ground truth label for classification, does not need subject testing, because you created this data set. You know which image is distorted by what. So you got enough data of the classification label. You train that, use that label to train subtask 1, just do classification. So once you are done with that, then you use that as starting point, right? So to train a subject task 2, so to do quality prediction. In this case, you only have a very limited sample with ground truths, right? So that's the first approach. There are also other approach. So that's based on ranking approach. So basically, you got when you do subjective testing, you got a much better kind of consistency if you ask people to rank, or just to show their preference, show them 2 pictures, ask them which one has better quality. So in this case, people got a much more kind of consistent answers. And sometimes you can also get a rank of these image quality without subjective testing. So for example, if you assume that I compress more, then quality get worse. So I do JPEG compression, I can compress more and more and more. And then when you do the experiment, you can assume that the image that got compressed less always has better quality than the image compressed more. So if this assumption is correct, then you basically don't need to do subjective testing. So you can have this ranking data. You throw that into your training process. That would easily create a huge amount of training data without doing subjective testing. So you see all these tricky stuff, all these tricks, it's trying to kind of reduce the number of the necessary subjective testing, right? So we also have papers to talk about that, how to train a model starting from we call it discriminable image pairs or discriminable image lists. So discriminable image pair means that you have pairs of images, you have ground truth labels, but which one has better quality, but without doing subjective testing. So discriminable image list is like you have 3 or more a list of images because of some certain things I just mentioned. You know number 1 is better than the number 2 is better than number 3. So you can use that as a ground truth to train your model, right? So that actually is quite effective. You can use that to create a huge amount of kind of good quality data. They may not be exactly the ground truth, may not be 100% agree with human perception, but it's kind of close and it's kind of reasonable. And just by doing this, and maybe use the true subjective testing data as a final tuning step, that actually help a lot. Especially when you don't have enough data, right? So in that case, this approach is very effective, that you got a lot improvement in terms of quality prediction. So another thing is we can also synthesis kind of benchmark kind of not real ground truths, but kind of synthetic ground truths. So for example, if you are trying to train a no reference image quality assessment model, but you know full reference image quality assessment models are working way better than no reference models, then how about I have a collection of the best performing something proven in the literature, the best performing full reference image quality models. I somehow kind of combine them and let them kind of to select which image is better than the other. Through this, I don't need to do subjective testing, but I can make use of the full reference model to create a lot of kind of synthetic benchmark or synthetic ground truths. And then I can use that. In this case, we can create millions of training samples, and then we use that to train a no reference model. So that's another way that can, we have papers talk about that, and it's very helpful. Right. So, okay. So having said that, I want to talk about something probably a little bit more interesting. So it's separate from the things that I have just talked about. So it's called model comparison challenge. Actually, this is also a data challenge. So why I say that? Because in this case, what we're given is a measurable quantity defined on a prediction domain, right? So it could be something you can physically measure, right? So it's something you can measure, right? So image quality, of course, is one good example, right? Image quality you can measure by doing subjective testing. Suppose you have a measurable quantity in a prediction domain, but you want a model to predict that quantity. Given any sample in that prediction domain, you want a model to predict that measurable quantity. And for any given sample in the prediction domain, multiple computation models are available to predict the quantity. So basically, you got a sample in that prediction domain, you got 2 or 3 or even more models. Each model speaks something, right? So they say this sample, based on this, when I look at this sample in the prediction domain, this is my prediction of that measurable quantity, right? So, and the measurement is associated, the physical measurement is associated with a cost, right? So, in other words, it's easy, it's very cheap for you to starting from the sample and compute a prediction. But in order to verify that, you need to take that sample, do the real physical measurement. That could be that could have a high cost. So then the question is, which model is better? Of course, you can, if you do a lot of measurement, you know which model is better. But the challenge is, can you give me the answer with minimal cost, right? So just to give you one example, suppose you are giving a piece of land, right? So it's a big area of land, and there's and then you're hoping to get the oil out of the land, right? But that you have to know where in this whole area you need to dig a hole to get your oil, right? So then you have multiple models, right? So looking at this area, and different models have a different prediction. One model say you should, this is the highest possibility place you should dig a hole, and the other model is have a different prediction. But the problem is, what if you every time you dig a hole you spend $1 million, right? So that could be a problem, right? So if you don't consider cost, let me just dig a hole everywhere. So just dig 1 million holes, right? So and see where I can get the oil. But now you have a model to do the prediction. Maybe some of the model is really great, just tell you exactly where is the oil. But you at the same time, you don't want to waste your money because you don't know the model, whether the model is doing the right prediction. You have 2 or 3 or 4 model, they all make different predictions. Then I guess the first thing you want to know is to which model is better. If this, if I find the best model among the 3 or 5, I should follow that instruction and dig a hole at that position. So the question is, can I hopefully dig a few holes? Then I first figure out which model is the best, right? So you can, so this is a good example about a good application of this major problem we're talking about. It's a model comparison challenge, right? So so there are, of course, there are direct approaches to do model comparison, right? So what we can do is to sample the prediction domain, right? So you can have uniform samples, you can have random samples of the prediction domain, and then you make prediction, and then you do a measurement, and then you do a comparison. Then you, of course, by doing this, you have a result. But of course, by doing that, it's very costly, right? So that's a major problem. So there's another problem. There's a prediction accuracy versus the model complexity problem, right? So if you based on the principle of the Occam's razor, if two models is doing the same level in terms of accuracy of the prediction, then we should favor the simpler model. But this actually is a little bit complicated. Just regardless of whether this Occam's razor is a good principle that is very useful, that people have been using that and very successful, but it's kind of like a philosophical statement. There's no scientific proof of that, right? So just forget about that. Suppose this is okay, but still there's quite a lot of different things. And then you can also talk about the minimal description length. You can talk about Kolmogorov complexity when you compare the complexity of the model. So the complexity of the model is not some simple thing you can do, right? So whether one scalar value as a parameter is simple enough, but one scalar value can also contain infinite amount of information in there, right? So whether this minimal description length or Kolmogorov complexity is the best measurement, but say Kolmogorov complexity itself need theoretically in the infinite amount of time in order to figure out what's the actual complexity, right? So there are many complicated stuff in there, right? So I don't have the time to go through all of them, but basically there's some problem. There are some traditional way of doing model comparison, but there are also problems behind that, right? So, and then we come back and think about this problem again, right? So the reason why we have all this trouble with this data challenge of model comparison problem is actually because we're trying to approve a model, but trying to approve a model is actually super difficult. So this is actually coming from the philosophy starting probably from David Hume about this induction problem, because it's impossible to prove a model without exhausting all samples in the prediction domain, right? So you have seen a million kind of swans that are all white. You cannot prove all swans are white, right? So but when you see one example, the interesting thing is when you see one black swan, then you disprove model. So basically, to disprove a model is easy, right? So this is a deductive method. It is possible to kind of disprove a model with one single sample. I think in the early days of the 20th century, so we have super famous, the most famous physicists in the world, when they argue with each other, right? So when Einstein, right? So when they argue with each other, so you can see what's their behavior. So they are not trying to prove their model. They are trying to find enemies and then disprove others' model. So then you think about what's the method they have been using to defeat others, right? So you think about that, right? So to figure out the simplest way to do that is to find a counter example of the other of their enemy, right? So which means they exactly follow this general thought. In order to prove I'm right is impossible, it's so difficult. But I just want to find one counter example to prove you are wrong, right? So that's how you defeat others, right? So that's basically actually the fundamental motivation behind our MAD competition, what we call the maximal differentiation competition approach. The only difference is that in the old days, when these super famous physicists, when they argue with each other, it takes the smartest mind in the world in order to find a counter example. They have to construct that counter example in their brain, right? So, and you have to be super smart, have to be smartest person in the world in order to construct that counter example. But can we do something lazy, right? So how about we construct those counter examples automatically, right? So this is the basic idea, what we call the maximal differentiation competition approach. So yes, in order, instead of trying to prove a model, we're trying to disprove a model. So basically what we do is to select an initial sample, we do prediction, and then we do prediction by two models. And then after that, we find a pair of samples that maximally differentiate one we will call the attacker model while holding the other model fixed. So basically, we go to the prediction domain, starting with 1 point. From 1 point, we can measure that, say, image quality or other quantity with 2 models. Then we are trying to search around that point, right? So trying to find a pair of samples that hold one of the model fixed, but maximally differentiate the other model. And then we can switch the role of these 2 models. We've got 2 other pairs, right? So then in the end, let's compare these pairs, because these pairs is like one attacker model trying to fail. That's the exact counter example trying to fail the other model, right? So let's play that game and see which model would win, right? So hopefully one would win, or maybe both fail. That's also possible, right? So I'm gonna skip this toy example because I have talked about image quality assessment as one already, so you know the problem, right? So here actually it's kind of like that, right? So because you have all of these, you're holding mean squared error to be fixed, right? So like all these 5 distorted images have the same mean square error. Then you want to maximally differentiate. Here I cannot say it's maximal differentiate because I'm still trying to construct certain examples to fail MSE. But here we already got idea to fix mean squared error and trying to find some example that have bigger structure similarity measure or lower structure similarity measure. But here is the real thing, right? So let's just do that, right? So just follow exactly what we have talked about this MAD competition. So we have a reference image in the middle. We kick out by adding some noise. Okay, that's our initial image. And then, if for all the images that has the same mean squared error respect to the reference image, in that image space, it's going to be a hypersphere. So how about we search along this hypersphere, trying to find the image that has the best structure similarity and the worst structure similarity. And here's a real example. That's exactly how we start from 1 point using kind of a gradient-based method to move towards direction to improve structure similarity and finally converge into an image. And then we also go to the direction to kind of get to kind of reduce structure similarity and then also converge into a point. So if you can look at the top image and the bottom image, they have the same mean squared error when you compare with the reference image. And then they have very different quality. The top has extremely good quality and the bottom has very, very bad quality. Whereas all of these pictures along the sphere, they have the same mean squared error, right? So the interesting part or the difference of this, when you compare this with the previous Einstein example, is that here, when we find counter example, we do that automatically. We use algorithms to search the best counter example. So that's the difference, right? So that's what we call the MAD competition, maximal differentiation competition method. So this is, again, just do some original image, initial image, and find the best structure similarity and the worst structure similarity. The worst structure similarity for a fixed MSE is always got this kind of funny picture like the bottom, but they do have the same mean squared error with respect to the original image, right? So, and then you can do the fair thing. You say, let's fix structure similarity and find the best MSE and the worst MSE. So MSE is saying that the left image has the best quality, the right image has the worst quality. But most people would think the opposite. But in any case, they all look very, very high distortion. So, and then we can do this with more. We can start with different initial point by adding different amount of noise, and then we'll run this MAD competition approach, right? So basically, that's a summary of this MAD competition approach. Select an initial image, predict by. Sorry, this is a group. Sorry. So. And we can do this further, right? So because in the previous example, we only have 2 models. Suppose to have a group model, so have more models. Then we can select an initial image, make a prediction by multiple models, and then we can find pairs of this MAD competition approach. And then in the end, we can aggregate all of them together and trying to do assessment. That's what we call the group MED competition approach, right? So we run this through the image quality assessment and example that include many full reference models and no reference models. And then once we pick those pairs, then we can do subjective testing, asking people, this is a pair, which one has better quality? So for that, after that, we get a pretty consistent result. And then we run many different image quality assessment models and end up with certain measurements. One thing is called resistance. Resistance is the measure about how robust of a model as a defender, right? So other models trying to defeat me, right? So but sometimes they fail, right? So then we kind of got to record, right? So that's and then we aggregate all these pairs of comparisons, and we find which one has the best resistance, right? So and then another measurement is called aggressiveness, which is how successful. Suppose my model is an attacker, attack all the other models. How many of them I can fail them, right? So that's and then you put them together and do a statistic. That's what we call the aggressiveness, right? So this is the result we have when comparing kind of well-known image quality assessment models, right? So I think it's time. I have to wrap up. We don't have much time for questions. So to summarize, we talk about the data challenges as a common problem, and then you can use traditional way to solve the problem like data augmentation or transfer learning type of approaches. And we also talk about this model comparison method, especially math competition and group math competition approaches that basically change the philosophy from trying to prove a model is right to kind of try to disprove a model. If a model, basically the idea is if a model is hard to disprove by all competing models in the same field, probably that model is a better model, right? So and then we figure out this can save you a huge amount of time, samples, right? So and largely reduce the cost to do model comparison. Right, so I think I had better wrap up at this point. Thanks.
Thank you for your talk. So if anyone has question, you can at this point ask directly, and I think everybody can talk. So please go ahead if you have particular questions.
Do we have anything in Q&A or okay?
I asked the two questions, and then there's this comment which is not a question, but I don't know. I can just read it. I study evaluation of text generation and image quality assessment has many analogs to our area. One thing we found was that in deciding which model is better, humans are unbiased, high variance estimators of model quality dependent on the number of samples you can use, while automatic evaluation was biased, low variance estimators. You can automatically evaluate a lot more samples. Because of this trade-off, moving forward in evaluation requires intelligent combination of automatic and human evaluation.
Oh, so there's no question, but this is very interesting comments, and yeah. So yeah, I guess it's like a common problem that probably exists in many fields, right? So here I'm just using image quality as a example. And when I talk to people, say people working in the medical field, that's like data is the king, right? So most of the problem is because you don't have enough data. It's so expensive to get data to train a model. So for machine learning people in the real world, in most my experience is in most cases people are struggling with data rather than models. That's my impression in most real world problems. The only very few, like say if you do Go game, yeah, okay, probably you have a way to collect quite a lot of data, but for problem like image quality and like a medical field is super difficult just to get enough data, even reasonable kind of data to train a model.
Yeah, I was working with on some problem in medical domain, and sometimes even having 100 annotated samples is challenging.
Yeah, that's right. Yeah. And there's capacity issues with the doctors, and there are also privacy issues and so on. Yeah, so and the accuracy and so on, and that's really complicated. So at least image quality assessment, you can at university we can have 30 students there. But in the medical world, how can you get 30 doctors to help you? That's gonna be very difficult.
Right. Okay. Thank you so much for your talk. I guess there's no additional questions, and at this point, I think we can end recording.
Okay, thank you.